I want to jump back to two things that you saw before. You got to see two sort of common reports that you guys are getting or should be getting. I'm actually hearing another customer speak about, hey, I've never even seen that combustion test before, and I'm assuming it's being done. The intent of that first part of the workshop was to do two things: help you guys understand the sources of loss, the main sources of losses in the boiler, and to show you the types of things that are out there today that you're already doing that can help you quantify those losses. And so now you've seen, Mark went through in a very detailed, you guys got a 10-minute, 15-minute crash course on water treatment for boilers. So now when you get that water treatment, it shouldn't be so foreign to you. You know, you should be able to read through it. And there's some great pieces of information. I had one customer who consistently had out-of-spec conductivity, and he went an entire year without actually reading the report. And on top of that, there was a direct recommendation from the water treatment service provider on how to correct it for the entire year, month after month. But because the guy got the report, filed it and never read it, he actually wasted and had way more blowdown. Basically, his blowdown valve was open 24/7. So it's worthwhile reading these reports. They're not generated just to kill trees. The makeup water that's on the report is also something very important. Mark talked about, especially if you get it historically if you get a trend from your provider, typically they'll at least say, hey, what was last month's? But if not, if you start to trend it yourself, this can be great indications of steam traps that are failing, condensate loss or increased condensate loss for whatever reason, failed condensate receiver systems. If you guys have multiple pumps around the facility where your condensate goes and then you pump it back, this is the type of reports that you want to be viewing to ensure that this stuff is still functioning in the manner it was designed. So that's one important report. And then the other one was the combustion strip. So somebody else spoke about Miura boilers on the break. One point to note with Miura is that they don't necessarily provide you with the combustion strip. In their service report, they have a little side section on the right-hand side which says, hey, here's how your boiler's combustion is. And it's pre-written, and the service guy will go and fill in each of the different fields. It'll have flue gas temperature, CO, O2. It'll have everything that was in the combustion strip that we talked about. It's just not physically the strip that you're handed. Other guys will give you photocopies or they'll give you the real thing. So now we should be reading that strip and putting it away after we know that everything on there is okay. Now we're going to shift gears into energy savings opportunities in boilers in the boiler room. We are going to stay a little bit away from the steam system, but I do want to touch back to this plot where we talk about the energy flow versus our energy saving strategy. So yes, I'm saying we're going to stay in the boiler room, which is a little contradicts what I said, but I do want you guys to remember this plot because you need to start from here. Before we go ahead and do things like economizers or improving the boiler, a new boiler, let's make sure that every pound we're sending out is how much we need to be sending out, and we're transferring it there as efficiently as possible, that we don't have uninsulated lines. We're doing our regular steam trap audits so we don't have steam blowing through. We have clean heat exchangers, we don't have scaling, we don't have water in there, etc. Then we'll start talking about the energy converter. So just 2 points, if you guys recall our boiler system, we're going to work with that 300 horsepower boiler, because as we talk about different opportunities, I'm going to throw a few numbers at you guys in terms of cost savings, typical simple payback periods, and it'll all be based on this sample boiler room that we talked about. So just briefly about the steam distribution, and it's not the focus for this workshop, but we do want to minimize the steam requirements in the facility from the get-go, which can be done with things like lower set points, lower temperature set points, lower pressure. Do you need to be sending 150 psi steam? If the minimum process need is 78 pounds, yes, you don't want it dropping below, but you need to be generating it at 150. We saw the temperature versus pressure plot. So the higher the pressure, the higher the temperature, the losses will be linear with that temperature. So we don't want to be going down that path of generating. It's like you guys wouldn't do it with compressed air. If you needed 80 pound or 90 pounds with compressed air, how many people here are running their compressors at 150, 140 pounds? Everybody's down in the back. It's the same with the boiler. You need to understand what the user is, and then you can work on with your pressure. We want to make sure we have efficient heat transfer, as we talked about. And one thing that you can see, the nice little stand-up sign, we have our energy solutions portal. And on that portal, there are things such as a steam insulation calculator. So if you guys aren't already registered for the portal, please do. It gives you, there are a few sample calculators. I think there's about 5 or 6 calculators on there currently, and we will be putting more boiler-related calculators on that portal. That portal is a way for you to do a quick sanity check. Hey, the guy came in and told me I'm going to save $50,000 by insulating 150 feet of 3-inch steam pipe, and my steam pressure is 100 psi. Well, according to our calculations, which are based on science and heat transfer, you're going to save about $6,000. So now at least you can frame up, is this a 1-year payback? Is it a 2-year payback? Is the guy totally out to lunch, or is he being pretty honest with me? We have a few calculators that do that for things like air compressor heat recovery, ventilation, and air doors is another example. So in your package is a portfolio card, or in your portfolio is a little card which has the address where you can go and register for that portfolio or for that portal. So please go ahead, sign up, and you can use this as your preliminary start for looking at opportunities. And then you can actually even log if you want, if you say, hey, this is looking good, I want to generate an opportunity, you can click a button and that'll go to your ESC and he'll give you a call, he or she will give you a call right away to look into that opportunity further. So back to the losses, and let's draw our box again around the boiler room. We've already said there are 3 main losses. 2 of them are much bigger, and we're going to focus on that. And the only way we're going to become more efficient is by reducing the losses we talked about. So first, let's go back to stack losses. We said it was the biggest one. Typically, just through the combustion process you saw when we did that example with your combustion strip, roughly 20% or 20 of those 100 fuel units leaves through the stack. So this is a great spot to start. Start from the biggest hitter, because 10% improvement here or 5% improvement compared to working on the blowdown, you want to start from your biggest losers and work forward. Stack losses, we can reduce the stack losses in 3 main ways. We've already seen with our combustion chart, if we improve our combustion, we got to make sure we don't send too much excess air through. That's going to help us have more efficient combustion. We can reduce our flue gas temperature. So the top part of the combustion chart was flue gas temperature minus combustion air temperature. So if we can reduce the flue gas temperature, then we'll also end up improving on the efficiency. We can do this through economizers or heat recovery. The last one is just a bit of a softer point, but you can also increase the combustion air temperature. So we said the top axis was the flue gas minus the combustion air, and the lower the delta T, the more efficient. So if you preheat that combustion air, you can also improve efficiency. So this could be as simple as running a duct, like a non-intrusive duct along the side of your boiler room near the combustion blower, so it sucks its air from the top of the boiler room where it's maybe 110 degrees. If you have a relatively tall boiler room and you go up to look at your DA and it's pretty smoking up there, 105, 110 degrees, that gains you 20 degrees, that may be able to gain you 20 degrees F on your combustion temperature. And you can use your combustion chart to see how much more efficient that is. And that way you can calculate a payback and what it's worth. Let's focus in on the reducing of O2. Excess air, we said, goes for a free ride. Those 7.52 parts of nitrogen, they don't react. The more excess air, we need to have excess air to be safe, but the more the less efficient you are, and the more that goes for the free ride. How much excess air, we had given you some rough percentages, but it does depend on the boiler itself. So your boiler tuner, who's probably doing the maintenance, this is where you want to be looking at the combustion strip and questioning them, hey, I see I'm at 8, 9, 10%. Why are we there? Can we be lower? Do we have to be on the safer side? Have you seen what's quite common if you are at 8% and maybe you have a vapor power boiler or another boiler with a burner that may not mix the best, you could end up at 8%, and when they dial it down below that, they actually start to produce CO. So talk with these guys, use the combustion strip as your common point, and see what's going on with the boiler. What is this worth? So let's say we had our boiler running at 8% oxygen, which is 78.9, and we brought it up to 5% oxygen. That small percentage increase is worth about 17,000 cubic meters per year on our sample boiler room. It's about $5,000 a year. Yes, this isn't, nobody's jumping out of their seats, and I'm not surprised, but this is also minimal cost. This is the guy, if you have linkageless controls, this is a guy just slightly adjusting the air fuel mixture, or if it's linkage controls, which we'll get into next, he's just dialing it in a little bit tighter. This is simple, low cost, and just by asking, you may be able to get a few $1,000s for free, more or less for free. The next way we can improve on our combustion is to make sure that we have a good control system. The purpose of combustion controls is basically safety and that air-fuel mixture. We want to make sure that we have the right air-fuel mixture depending on how hard the boiler's firing. So the boiler has a little gas pedal, and for all the different spots on the gas pedal, as we get more load or less load, we want to make sure we're dialed in with the right air-fuel mixture. Those controls, as your load changes, are what tell it where to go along the gas pedal. So it's basically what you do when you're driving, or if you have a newer car with the self-adjusting cruise control. The boiler has a control system which is trying to maintain your pressure, and it's going to change the gas pedal. That's what our combustion controls are doing. There are two main types. The first type, which is an older type and quite common still that we see, is a linkage combustion control system. A linkage combustion control system takes that pressure signal and says, hey, I need more or less steam, which drives a primary actuator motor. There's just typically one, maybe sometimes two, but basically one motor attached to a series of linkages. This can be 2, 3, 4. For some customers, this linkage can actually be the whole length of the boiler on some of the older thermogenics. Those linkages then actually adjust our air-fuel ratio. So you have multiple components driven by this one motor that control that ratio. There can be as many, or typically at least 10 little set screws for each of the different points. So there's a cam that's actually attached to all these linkages, and as they go through the firing rate, the guy's sitting there with a little screwdriver trying to dial in. He's got his flue gas analyzer, and he's trying to dial in your combustion. This system is on the way out. This is kind of our equivalent of carburetor in your car. They tend to build in a little bit more safety because these linkages can wear. So there's hysteresis. So essentially, as you go up and down the firing rate, that slop that develops in the linkages over time, there is some slop just from the get-go, but that slop means when you go back to the same gas pedal position, you actually end up with not the same air-fuel mixture. So you get something called hysteresis. You can also end up with less turn-down ratio with these designs. And they typically err on the high fuel ratio, like a little bit more excess air, just because of that slop. because when they tuned on the way up, maybe they got 6%, but on the way back down, they can't be below that 3-4% marker. So because we don't have that nice digital dialed in control, we're going to build in safety margin. And we know that the safety margin equates to more energy used because we're sending more air through. Here's a plot that I actually worked with a colleague of mine on for a customer where we took the boiler up through the different firing rates. So what you can see is they're dialed in around 6%. And as I said before, the lower firing rate, you get a little bit more O2. As per design, you have a little bit lower air velocity in the burner, so you have to throw a little bit of excess air to maintain flame stability. This is what we mean by hysteresis. On the way up and on the way down and on the way up, we ended up in this range, and this is actually where the customer tends to operate. We ended up with different air-fuel mixtures for the same firing rate. So this is hysteresis. Linkage-less controls is the car equivalent of a fuel injection system. Instead of all those crazy linkages and stuff, what we have is that a controller, they tend to put a different controller in than what you're already using, which takes that same signal saying, hey, I need more or less steam, which then sends just an electronic signal to the gas and air valves, and there's servo motor or servo-driven valves. So no more linkages depending on the other and having one motor. We have individual control valves that are digitally being told how far to open. So now we can go through the entire firing rate and say, we want this valve at 38.34%, and at that same point we need our air valve or the damper position on our combustion blower to be at 47.78%. So this allows us to dial in every point. There's no hysteresis, and there can be additional benefits such as improved turndown ratio. And because we don't have that slop to worry about, we can also dial in closer to that 4%. We don't need to build in that extra buffer because of the repeatability with the digital system. So on the left-hand side, you can see what I was talking about. You'd have this main master motor, and you can see the different linkages. So this one, instead of cams and little set screws, it has basically like tie rods, which we would adjust the position of the tie rod to set our air-fuel mixture. On the right-hand side, you can see the two servo motors that would do the same job. So one controlling the gas and one controlling the damper position on our air. So this is these fuel air ratio controllers. This is the digital version, and this is what we're talking about when we say linkaged versus linkageless controls. How do we save energy when we go to linkageless controls? We save energy by removing the losses we had before. So losses associated with the hysteresis, if we ended up at multiple firing points, so you saw that spread of 3 points, now we're always at that bottom point and likely slightly below it. We can reduce our excess air. We can dial it in closer. And if you have significant boiler cycling and there's the ability to improve the turndown ratio is kind of how much gas pedal we have. Do we only have a 3-to-1 ratio, which means we can only go to a third of the maximum firing rate? That's how low we can go with our gas pedal. You can have an increase to 10, 12-to-1 turndown ratio when you go to linkageless controls. That's burner dependent, but that is one advantage that you can have when you go to linkageless controls. Linkageless controls with those two servo motors is pre-programmed, so it's still an open loop system. A guy still comes in and dials it in and says, this is your setting. If your boiler, if you end up with more scaling, things like that, it can drift a little bit. But you can also buy the closed loop option, which is a little bit less common on small to medium-sized boilers, which is called O2 trim. And now we're into closed loop control, similar to when your car can run in both open loop and closed loop with the O2 sensor in the exhaust. This is the same idea. They put an O2 sensor in your stack, and then they say, yes, I should be at 44 and 46%, but things have changed a little, so I'm actually going to make it 44 and 46.3%. And that just keeps you even finer dialed in. This is less common, but that's sort of like the Lincoln versus the Ford model. If we go to our 300 horsepower boiler, this is a common example that we would see for linkage-less controls. So based on the age, we have a linkage-less controls calculator, and your ESC can work with you to determine these parameters. There's 0.5% loss today, or in the base case, due to hysteresis and the slop in all those linkages. They were operating around 8% or so, and now we're able to go down to below 6%. So we see a 2% efficiency change. Actually, this is closer to 10 to 6%. We see a 2% overall efficiency change in the combustion. So you can use your combustion chart and say, oh, if we went from, let's say we're at 10 and we're able to get down to 6, or 8 and able to get down to 4. And increased turndown. So this guy maybe already had a 8-to-1 turndown ratio, and we got him to a 10-to-1, which is going to give us a little bit less cycling, and therefore a little bit less losses associated with the boiler turning on and off. The annual estimated savings would be about 30,000 cubic meters, which is about $8,000 a year. Per boiler, an average install cost is about $15,000. That would be my experience on a linkage-less control system. That gives you a simple payback period of still below 2 years. Working with your ESC, who would help you develop the base case and ensure that you have the accurate savings, you will receive our Enbridge incentive, which in this example, based on our 2014 program, you would get almost $6,000, dialing that into just a little over 12 months. And the maintenance side becomes simpler. We no longer have this guy kind of dialing in. We have repeatable air-fuel ratio within our boiler. Does anybody have any questions related to linkage-less controls? Yeah, it's an open loop. It's not like you see them start doing this. So you can have, if it's not set up properly, then you could see them start to wander a little bit, but they tend to be relatively damp systems. I've never seen an O2 trim system myself. You may run into that scenario, but I doubt that they would allow them, but I can find out for you. So it would be whoever your boiler service provider tends to. There are a few different providers that can help you out, or solution providers for this. I would work with your ESC and establish what this opportunity is worth. So we can see how much slop is there in your system. What's your current O2? Are you already dialed in at 3.8%? And what's your load like? Because hysteresis is more important if your load varies a lot. If you are constantly pulling, if that boiler pretty much stays at one point all the time, 24/7, hysteresis becomes less important, because then the linkages aren't really moving. So it's important to understand your base case. Does that answer your question? So some vendors would claim 10 to 15% savings. We tend to see 2.5 to 4%, maybe 3%. It depends on the base case. The 10 to 15 could be plausible if you have very poor O2, you're up at 15, 16%. But then I would question why are you up that high? Is it burner design? Because if your burner's not capable of going below that, because it's a poor burner, it's an old burner, there's bad mixing, just because you switch to the digital system doesn't all of a sudden mean you get better mixing. It means we can control it better, but it doesn't necessarily mean that we can go all the way down to 3%. So you need to establish the base case performance to evaluate exactly how much losses there are. So this goes back to the whole recurring theme of the presentation. The base case will tell us how much stack losses or how much combustion losses there are and where they're coming from. Then we can work with how to remove those losses. Most importantly, work with your ESC, who are here in the white shirts, to help you establish that base case. I would start with the combustion test, and depending on your scenario, we may come and do combustion testing as well. Ideally, what you would do is go up and down the firing rate. If you have an ability to vary the load, then you would want to see the combustion test over the entire firing rate. to have the best analysis. I would say a good starting number for any system would be 2.5%. If you know you will save, if you start with that and it makes your payback period in an acceptable means, I would work with just a combustion strip. If you're not sure and you want to have more detailed information, work with your ESC and we can help you out. Any other questions with linkage list controls? Another way, as we talked about, of reducing the stack losses is to do flue gas heat recovery. We'll talk about two different types of economizers which are used to recover heat from the flue gas and put them back into an appropriate heat sink. The first one and most common that we see and is typically sold with your, if you bought a new boiler, it's very rare that you wouldn't get this option, and you may already have this, is a feed water economizer. So if you remember our boiler system, the feed water left the deaerator and went into the boiler. This is where we're going to talk, this is the location where we'll be working with our feed water economizer. Here's the same diagram, just removed a few components. At 8 psig, your feed water would be in the neighborhood of 230 degrees F. So as is today, without the feed water economizer, we're going to send that feed water straight into the boiler. The boiler now has to do the sensible work that we talked about, plus the latent phase change. If we introduce a feed water economizer, we would put it in the stack, which then we would pipe our feed water into the feed water economizer to recover heat from the flue gases, increasing the feed water temperature before it goes back into the boiler. So in this scenario that we've modeled, your feed water would be 230 degrees F. We've helped it do 37 degrees F of sensible work. We've helped out the boiler. Your flue gases were at 450, now they're down to 320, which is also going to mean when you look up the delta T on your combustion efficiency, we're actually extracting even more energy if you draw your control volume around your feed water system in your boiler. Is that straightforward with the feed water economizer? Yeah, so for the same surface area, for the same feed water economizer, if you had, let's say, 550 degrees F, I would expect that this would also increase. So instead of maybe, here we have a 130 degree drop, you'll end up with a more than 130 degree drop. Typically, we see between 100 and 125 degrees F with standard boilers, but yes, if you're on the higher end, and you can be on the higher end due to pressure or due to the boiler and the burner design, then you can pull more heat out for the same surface area. That change in efficiency, we can look on our combustion chart to see what that did. We were originally over here at 380 degrees F in delta T, and then we took out 130 degrees, which is about 250, so we'd be somewhere in the middle there around 84% efficiency. So we extracted about, 3.3% of the extra energy out of that thermal energy provided by the fuel. If we were to install this on our 300 boiler horsepower, throw some actual numbers to it, if we were 50% loaded in 6,000 hours a year and we did the 450 to 320 degree F design, we would recover on average about 210,000 BTUs per hour. That's how much extra heat we're going to pull out of the flue gas. This is worth about 44,000 cubic meters per year. And on this boiler, an annual savings of $12,500, or about 4.2% of the average load. If your boiler is bigger, more hours, more loading than what this is, you can scale this up appropriately. The estimated install costs that I've seen on average for boilers is about $25,000 installed on regular time. That's a simple payback period of 2 years. With our incentive, we can bring that down to 1.3 years, below that 18-month cutoff if that's what your facility is looking for. We will also help you evaluate what that's going to save. A word of caution that this 300 horsepower, 50% average loading, 6,000 hours a year, when you engage your boiler supplier on your feed water economizer quote, I would reference that part of the quote where they say, yes, we've modeled your boiler. You're going to save 100,000 cubic meters a year. What you'll notice is that they may have modeled a 300 horsepower boiler at 100% average loading for 8,760 hours per year, which may not be representative of your case. It may or it may not be. Working with your ESC, we can determine what these savings should look like for your specific boiler. Does that make sense? Does anybody have any questions with the feed water economizer? We don't provide necessarily 50% of the project cost. We provide the minimum of either 50% of the project cost or the calculated incentive based on what's inside your portfolio there. It's 20 cents a cubic meter for the first 50,000 cubic meters and 5 cents a cubic meter after that. So if you take 44,725 cubic meters and times it by 0.2, that's where the 8,945, so it would be the minimum of either 50% or the calculation of the savings. Is that clear? Again, you can work with your ESC who would determine the incentive. So if you remember on the first we don't work on the M&V method similar to maybe your electric utilities. We work on engineering calculations based on the information we can extract from your boiler, which we're equipped and have the expertise to do. And then our program, yes, we work on estimated calculations, but our program is actually audited to ensure that our estimated calculations are accurate. Does that make sense? The incentive would be provided, and we can take more, if you have more exact steps, we can take that offline too. But the incentive is provided after we see that the project is installed and functional. So if you decide to put in a feed water economizer and your maintenance guy decided he didn't want one and he bypasses it, then you wouldn't receive an incentive. It has to be functional. Yes. Does that make sense? If you have any other questions related specifically to the steps, you can work with your ESC, or I'd be happy to help you with some of those questions offline too. Let's jump to condensing economizers. So flue gas heat recovery can be done in two ways. We can use, and these options can be combined, and we'll talk about that. But first we talked about a feed water economizer. Now we're going to talk about a condensing economizer. If you guys remember back to the combustion basics slide, when we burn one methane molecule, we actually produce 2 molecules of water. So for every 1 pound of natural, or this is pure methane, in natural gas, our gas is about 95.5% methane, produces 2.25 pounds of water. That water is actually instantly vaporized at that flame. So we talked about, we spent all this time talking about energy, latent heat of vaporization, and that extra energy it takes. So the water that's generated through the combustion process is vaporized, and it takes those BTUs it takes to, or requires to vaporize, and that's part of the combustion process. It's roughly 10%, so 10 of those 100 joules we're putting in just goes to vaporizing that water so it can leave through the stack. If we were to cool the flue gases down below the dew point, we would actually condense out that water vapor. And as you recall, then we can recover that latent heat of vaporization. We can get that latent, the high heat part, out of the flue gases. The feed water economizer stays above the flue gas dew point and is just sensible heat recovery. When we get into condensing economizers, and the term condensing comes from actual condensing of the flue gases, getting those water molecules that we sent up the stack, and we'll actually generate water, as some people in the room can attest to. A condensing economizer will actually generate water out of this device. So we get two, when we install a condensing economizer, we get both forms of heat. We get the sensible, because we pull it down from wherever point it was to that saturation point or the dew point of the condensing economizer, and then we cool it further to actually condense out and get that latent heat. This chart shows you the flue gas exit temperature and combustion efficiency. So if we work from the right-hand side, this is where our feed water economizer. Feed water economizer, as we saw in that scenario, we're out at 330 degrees, so that's even over there on the wall somewhere. We would work from this side, and until you get to that dew point, the inflection point there, we're doing sensible heat recovery only. Once we hit roughly 137 degrees F, we'll actually start condensing, and you'll see this exponential increase in combustion efficiency associated with pulling that latent heat out. So if we want to get your boiler to 98% efficient, we have to get those flue gases down to room temperature. So even let's say we want to go to 96% efficiency, you're looking somewhere to have exit temperature below 100 degrees F. You can touch it. You can put your hand in it. It'll be likely a plexiglass or a fiberglass stack. It doesn't have to be steel anymore. We have to cool them down to get that sensible heat. Does that make sense? That critical inflection point is that point where we shift and we start condensing, and that's the mode we want to get into. This works. This is the same chart that works if any of you guys have direct contact hot water heaters. They work in the condensing mode, and the intent there is you can actually look at how efficient your condensing or your direct contact hot water heater is running by using this chart, and your flue gas temperature will be roughly close to your inlet water temperature. So if you're pumping in 80-degree water, that unit should be somewhere near the 95, 96% efficiency marker, because we're taking advantage of cooling those flue gases down below the dew point. That same chart, if we look at the quantity of sensible heat versus latent heat, so sensible without the condensing is represented in the gray, you can see how much the latent heat plays into the amount of heat available. So if you use 75 degrees as your reference point and say, we're going to cool our flue gases down to 75 degrees, more than 60% of that is latent, and the rest is sensible. So we need to get that down to below the dew point and start extracting that heat. We use a condensing economizer to do that. So in this scenario, I've taken our regular boiler room, but I've actually bumped up the makeup water a little bit higher. So let's say we have a process where we're producing kosher food and we can't return the steam. Now we actually only can get about 25% of the condensate back. We have a little bit more makeup. Same diagram as before, but now we're going to insert an inline condensing economizer. Instead of piping the feed water, what we do is we actually take our makeup water, that's 75% makeup water at 50 degrees Fahrenheit, and put that through the condensing economizer. That's how we get those flue gases cooled. We would put them in, we would raise them no higher than 190, 200 degrees F to ensure that the deaerator still has a little bit of heating, that mechanical heating that Mark talked about. That's used for actual oxygen stripping, so we want a portion of that left for the DA to do. So we will heat it to roughly 190 degrees F before it goes into the deaerator. This is going to reduce how much DA steam that we're going to send. Or if you just have a condensate receiver and you don't have a deaerator, right now you have probably a thermostatic valve that's driving, it'll be set for, let's say, 180 degrees F, 190. As you throw in cold makeup water, that valve opens up a steam valve. It's allowing steam to come in and preheat that water. By using the flue gases to heat up that makeup water, you'll actually reduce the amount of steam either sent to your condensate receiver or your deaerator, or both, depending on what your piping system looks like. In this scenario, we'd reduce the flue gases down, I've just done for a sample, 100 degrees F. If somebody's proposing a condensing economizer to you and they are not cooling the flue gases, if the outlet flue gases is above 140 degrees F, you are not condensing. You need to get those flue gases down below that dew point to get the latent heat, and I can't stress that enough. So, because many people can propose that without getting to that level. So makeup water typically comes into the facility 50, 60 degrees, 65 after softening. So it's typically cool enough. Another thing you can use as your heat sink, though, it doesn't necessarily have to be makeup water. If your facility has high amounts of processed water, so let's say for food we have a ton of cleaning and processed water, hot water that we want around 150, 140 degrees F, and you're just heating that with steam, you can use a condensing economizer instead of makeup water. You can put processed water through here. We just need that heat sink to be somewhere in that be able to get the flue gases below the 137 degree F dew point to start extracting that latent heat. The carbonic acid that comes out. So typically, and we'll talk about that, I think it should be in the next slide, but we'll address it now. Most people dilute it with their blowdown water. So the degree of, or the acidity of that water, the carbonic acid, so what happens is that CO2 that we generated in the flue gas is absorbed during the condensing process. So you have a little bit of carbonic acid, you have a diluted solution, which then actually is coming out of that unit. So it is a water that is produced. So I said these units actually make water. We make water out of the air in the actual combustion process, natural gas, and there'll be a drain on here. Typically what's done is that is mixed with the blowdown water, and that tends to be sufficient for the level leaving the facility. So when your sulfuric or the sulfur content increases, they will self-destruct. But let's say you are a curtailment customer and you burn oil whenever we call curtailment. The one supplier of this device, when you switch it, you tell the condensing economizer that you're running oil, and it will bypass while you're burning oil so it doesn't self-destruct. Then, once you're back on natural gas, it has a built-in delay period to make sure that you've flushed out all the sulfur, and then it goes back into condensing mode. So if you run heavy fuel oils or high sulfur content fuels for many days throughout the year, then you need to increase the strength or the type of material you're using. You have to change the material. And that's a function of, like you said, of how much sulfur content. If you're just doing it for a few days of the year, then you can still use this solution because it has a built-in bypass. Does that make sense? No, typically it's just bypassed. That would be the typical solution. There may be other solutions. This mode can be combined with your feed water economizer in what I call an offline solution. So we have our standard feed water economizer, but we use an induced draft fan to pull flue gases off of the side of your stack. So we kind of put this unit beside on the floor. We pull from your stack, put it through the condensing economizer, and then have a new stack. So you end up with 2 outlets from your boiler. These two can be used in parallel. What this avoids by putting it not in line is you don't have too much of a pressure drop on your combustion blower. It also allows maximum flexibility. So our sample boiler room had one boiler. It had one 300 horse. If you have 3 200 horse boilers and you alternate them, let's say we usually have a lead, lag, and a standby, you can use this solution where we pull from 3 boilers and it detects which boilers are on basically by measuring the temperature in the stack, and pulls and uses dampers to pull from only the boilers that are on to preheat the makeup water. Same solution, I just call this one inline because it's in the stack and typically is not used in tandem or in series with a feed water economizer. It's just this unit, and this is used in series with the feed water economizer and is an offline unit. This is a more expensive option, but offers more flexibility. So your ESC can work with you to evaluate which option makes more sense for you. So quite often the maintenance department doesn't want to say this is going to be our dedicated boiler, and this becomes sort of a mandatory option if you have run multiple boilers with a lead lag standby. What you need to understand to make sure that you get a successful project and it makes sense for you is how much heat source is available, what are your flue gas temperatures, how hard is that boiler running, how much heat source, and is there sufficient heat sink? We need to put that heat somewhere to get the flue gases cold. That can be boiler makeup, it could be domestic hot water, if you have a sufficient domestic hot water demand. It can also be process water, as we talked about. I can't stress this enough, but you gotta get the flue gases below the dew point, and if you're not, then you're not condensing. I have a customer who installed a condensing economizer, and the drain is left open. The drain on the condensing economizer is left open right there, and I said, you can't do that. It's gonna drip on the boiler and corrode the boiler. He said, oh, nothing comes out of there. If there's no water coming out, it's not condensing. That customer used, I would say, a less efficient design mixed with a contractor who did not want to use that mode use that economizer as a condensing economizer. There's a big difference. You can't just swap these units and say, hey, I have a feed water economizer and lots of makeup water, so I'm going to start using it as a condensing, because makeup or feed water economizers are carbon steel. And as soon as you start condensing in that carbonic acid that's there, it'll corrode your feed water economizer. It's quite similar to cold shocking your feed water economizer. So if you've had one fail prematurely due to not being able to maintain your feed water temperature, that's cold shocking, and that's what would happen if you tried to use a feed water economizer as a condensing economizer. So the condensing economizer is made of stainless steel in order to make sure it can handle the carbonic acid. I don't want to scare you guys with the level of acidity that comes out of here. It is a weak carbonic acid, so if you drink Coke, Coke is also quite acidic. So you can have it tested if you are concerned, and you can work with your condensing economizer supplier, but I would say quite commonly it's either sent right to drain because you have so many other fluids that are mixing when it gets to the sewer, or mixed in with the blowdown. I think that's what you guys do, right, Tom? You mix it in with your blowdown? Yeah. What does this look like? What is it worth? Let's talk about an inline example. So if we had that 300 boiler horsepower, 50% average loading, 75% makeup, with that 300 horsepower boiler, 50% average loading, there's 1.1 million BTUs available of heat in that flue gas. More than 50% of that is latent. So if we just put in a feed water economizer and are only going to get the sensible, we only can get 500,000. Less than 500,000. This example only uses 7.4 GPM. So if you have a process water sink that is more than 7.4 GPM in a similar, which is about just shy of 4,000 pounds per hour, domestic water or process hot water, you can use this scenario. We only do a little bit of latent heat. We get about 75 to 80,000 BTUs per hour on this one. Annual gas savings of 120,000 cubic meters per year, worth $34,000 a year. Not bad. It's about 11.5% of this load. So we said this is roughly a 1 million cube boiler room. We're going to cut it by 10%. Estimated install cost for an inline is about $60,000 if you're doing a full retrofit. If you're replacing your boiler in your scenario, this is somewhat representative of your scenario either through process water or through increased makeup water, the installation cost is actually quite a bit less because you're already cutting all the pipes and the stack and such, so then really your install cost goes down to just the unit cost. In this scenario, you have a payback just shy of 2 years. Working with your ESC who will help you evaluate what this opportunity is worth for you. In this scenario would be worth $13,600, 1.36 year payback. So again, we're sneaking this below 18-month payback periods. These are tangible options. Ideal for food and beverage industry, anybody who has large amounts of cold water, breweries, textile, chemicals. If you're not returning condensate for whatever reason, that makes you an excellent candidate. If you have huge amounts of flash and you're dumping steam, that can make you a great candidate too. If your building's older, we don't get condensate back. It's a pain, it's costly to core through the building and get that condensate back. We can evaluate what it's worth to do the condensing economizer. The last quick opportunity we're going to talk about to end the presentation is the blowdown losses. So we said when you got to do the blowdown, we got to get rid of that sludge. And when it leaves, it's at that saturation temperature. Blowdown heat recovery can be used. And what we'll do is we'll use a flash tank and heat exchanger. As we talked about with the approach, ideally, first thing you want to do is make sure you're doing the minimum blowdown so you have the right chemical treatment, the right water treatment and water levels, so the conductivity level. Then we'll move to the recovering of the blowdown heat using a flash tank and heat exchanger. Our blowdown is fed into what we would call a flash vessel or a flash tank, which allows the two to separate. When we have the high pressure blowdown and it's exposed to a lower pressure, so let's say we had a 10 psi flash tank, a portion of that will flash and a portion will remain as liquid. We can take that flash steam off and send it to the DA or your condensate receiver where you're heating, where we were doing that makeup water preheating or doing the DA oxygen stripping with the steam. We can supplement that steam with the blowdown heat recovery. Then we use the liquid, put it through, let's say, a plate and frame heat exchanger, or it can be a simpler device to preheat the makeup water. We utilize the energy, like I said, for flash steam and preheating makeup water. This isn't typically, you don't have to go source these opponents. This is typically sold as a skid package. So they'll propose a solution which basically this is all encompassed on one skid. You have your blowdown input, your blowdown output, and your blowdown, your flash output, and your makeup water inputs and outputs, and you just attach them. No, so the heat exchanger is designed to be able to handle the sludge. So it could be a tube and shell. I've seen tube and shell. I have seen them with plate and frame as well. It is, so the pressure here on this side is your boiler pressure, right? So it's not a low pressure, slow release that comes out of there. When you blow down, if you have a 100-pound system, you have 100 PSI blowdown. One benefit, I don't know if you guys have blowdown receivers today with cold water makeup. So typically the city, whatever city you're dumping your sewer goes to, they don't really approve of letting that blowdown liquid at a boiling point go to drain. So you actually flood your blowdown tank with cold water. If you do blowdown heat recovery, you can nearly eliminate the need for that fresh water. And you're just putting nice, fresh, potable water most of the time, mixing the two together to get a diluted solution so that the drain temperature is sufficient. Typical savings that we see, this depends on how much blowdown you're doing. So if you have more makeup, you have more blowdown. If you have nearly no makeup, you have less blowdown. 1.5% to 3%. What does this look like for our scenario? 24,000 cubic meters, about $7,000 a year. For this size of boiler, the estimated skid package installed would be about $14,000. Bring in the incentive, 1.3 years. Again, we're looking at 14, 15 months payback period. Your ESC can help you, working with your water treatment, looking at your water treatment reports, determine how much your blowdown rate is, and thus how much heat. If, again, we can only recover the losses, so we need to understand how much blowdown you're doing in order to evaluate this opportunity. Let's talk about our limited time campaign. For a limited time, we have doubled the incentive on linkage list controls, economizers, and blowdown heat recovery to a maximum of $25,000 or 50% of the project cost. Work with your ESC if you're looking to get this stuff done. Work with your ESC and let's get this done now and take advantage of that offer. This offer, if we visit our feed water economizer, 300 boiler horsepower with that feed water economizer, 1.3 years. If we use the double incentive campaign, that brings it right, it's actually just a little shy of 12 months. So you can get extra money towards these initiatives if you work with your ESC now. To sum up, today we talked about energy savings starts by understanding the need, the requirement of what we want to do, and then working upstream. There are two main losses in the boilers. We can only save what we're losing, so let's dial into those stack losses and then the blowdown losses. Your ESC can help you better understand your specific boiler system. There's a lot of people who install them in very different ways. The guy who installed it for that reason is long gone, so everybody's unique. Let your ESC help you evaluate these opportunities, and let's get on them now so we can take advantage of this limited time offer. Thank you for attending the workshop, guys. There's also a survey, 2 surveys in your package. Sorry. Please fill out the survey and just leave them at the door. Your feedback is important to us because we want to design these workshops to be of maximum benefit for you guys. We also have a second survey about our programs because we want to make sure that the programs are designed to help you guys. If you think there's things that should be improved, please let us know. It's to your advantage to help us design the programs that fit your needs. Thank you, guys.